Hey everyone, thanks for joining me again on my YouTube channel. This is Workshop Quick Takes. Today, let's talk a little bit about resistive connections, something very near and dear to every Jeep owner's heart because these older Jeep vehicles, they don't have the greatest wiring, and of course the plastics are old and brittle, so by now things don't necessarily fit exactly as they should. And the most notorious one, of course, is the headlight switch, because the older models, including the XJ all the way through 2001, have direct control over the lights. In other words, all the current that flows to the headlights has to flow through that switch. Any modern vehicle, of course, that's done with relays under the hood, and there are kits you can buy in order to retrofit your XJ the same way, or other Jeep vehicle. Now, why does this matter? What's a resistive connection? Why does this occur? Well, you think about a 12-volt power port as an example. A 12-volt power port was designed about 100 years ago, sometime around in the mid-20s, I think, according to Wikipedia, is when they first started appearing in vehicles, because cars were becoming popular. Smoking was already popular. People wanted to smoke in their cars. So you can imagine that a power port designed to power a small little lighter accessory for very brief periods at a time might not be optimized for high current loads connected into a 12-volt jack. However, today we've got all kinds of things. Most people are just charging their phones off of them. But this here is a ceramic heater that's designed to plug into that, and it draws considerably more current. The reason I even have this and paid way too much for it at a truck stop was because a couple years ago during the winter I had to make a run out to a job site and we'd had some snow and ice. Well, that was around the time I was having trouble with my thermostat, which we documented in another recent video that you can watch. It was opening way too soon, the vehicle was running cold, I couldn't defrost my windshield, and I was 40 miles away from home and 40 miles away from the job site. What do? Well, I stopped at the truck stop, got that, and kept running it for short intervals in order to defrost the windshield. But I couldn't run it continuously because I'd start to smell hot burning plastic, and it was coming from a very, very hot power port. Alright, today's a perfect day to try and replicate what happened. Temperature's in the high 30s, so it's a little bit warmer, but still pretty chilly. You've got the heater. It's rated for 150 watts at 12 volts DC, which means it'll pull a maximum of 12 amps, and often these things are a bit optimistic, so I wouldn't be surprised if it caps at about 10 or 11. Looking at the inside of our power port, however, with the infrared thermometer that we've got, it says it's about 38, 39 degrees in there. And according to this is rated for 12 volts, 20 amps. Would I ever want to connect 20 amps to that power port? Okay, so we got everything set up here. Let's just start the stopwatch and let this run for about 5 minutes and see what happens in there. Two minutes in, the plug itself doesn't feel warm and I'm not smelling anything yet. 4 minutes, might be feeling a little bit warm, but I suspect the action, if it's happening, is happening back at the positive tip in there. Okay, we're at 5 minutes. We're going to cap this because I don't have all day and I don't want to let it actually melt in there like it's almost done a couple previous times. Let's just see what's going on. Well, look at that. We started at about 38 degrees and now we're in the high 130s. We added 100 degrees Fahrenheit just by running that little heater for 5 minutes. 150 watts at most, and it didn't change the temperature near much. Had all the other dash accessories shut off, the heater was off, nothing else was running, so there wasn't much else putting heat into that area. All of that temperature rise was coming from something that's happening in that port. What's going on? Where this plugs in, well, this here is spring-loaded, that's fine. This here is spring-loaded, that's fine, but it's basically just in there with friction. So as long as this can hold it in there tight and still depress this, you'll get a fairly good connection, but maybe you won't. And even if you do, is it enough to actually transfer the amount of current that your load can draw? Let's turn to the bench, do some quick whiteboard math, and see why power is dissipated in a resistive connection and how quickly it can increase. Typical circuit in a vehicle. Here's the positive source on your battery. You're going to have a fuse upstream somewhere, but let's just say that we're starting our analysis with the switch. And then your load, but I'm just going to draw something like a healthy light bulb. And then it returns to ground, chassis, which happens to be battery terminal negative. So that's over here also in play. This returns with very, very low resistance. We're concerned about this. This switch here and all wiring to our load, as well as whatever little tail comes out to the chassis return, does have impedance. And the OEMs will control that by specifying wire sizes that minimize that. But devices like this, or let's suppose we even had a little harness connector in here somewhere, and so that little plug existed, and the power had to pass through whatever resistance is in that contact there. All this stuff here reduces the voltage that's seen at the actual load that we are trying to drive. Under normal operating conditions, these should be not too much. If you look up a 10 amp 12 volt switch for automotive use, you should see something in the specs like maybe 50 milliohms max, which is 0.05 ohms. So let's suppose the alternator is not running. We're just going to use the 12 volt nominal. We have ground, or 0 volt here effectively. The whole 12 volts dissipates between here and here one way or another. Okay, so let's just suppose whatever our load is, it's a really big healthy load and it's pulling 10 amps. We have 12 volt, we have 10 amps, our load is burning 120 watts, and we have two equations we can get to on that. So the first one is Ohm's law, V equals I times R. This is volts, this is current, and this is the resistance of the load. And we have a second equation of Ohm's law that looks like this, and this is the power equals volts times current, VI. Ideally, our switch here has an impedance of at most 0.05 ohms, and hopefully less than that. Well, some of the voltage between here and here is going to drop on that, and that is going to be V equals 10 amps, which is our I, times 0.05 ohms, which is our R. 10 times 0.05 equals 0.5. So we lose half of a volt. What are the implications of that at that switch? Well, we have our P equals VI, so P equals 0.5 times 10 amps. Now in reality, we might not get our full 10 amps across the load because we're adding resistance in series, but let's just suppose that in this case 10 amps is close enough. 0.5 times 10 amps equals 5 watts. 5 watts is not nothing. Here, for example, is the old fuse-style dome light, which I think came out of the dome light in my XJ. Using this infrared thermometer and getting it right there on the barrel of the device, we're seeing right around 70.7 degrees Fahrenheit, and that is the expected temperature in here. So let's connect it. Now I've got the voltage turned down to about 8.6 volts on this power supply, so we're seeing just about 5 watts burning there. And let's let that run for, well, let's say just a couple minutes. So we can see that over here there's been a very slight decrease in power, 4.97 watts. We were reading about 4.98 originally. That's an effect of the resistance of the filament increasing slightly with temperature, if I remember correctly. The infrared thermometer still says we're looking at about 70 degrees on the black background there. If I come over to here, however, depending where I hit it, somewhere between 100 and 105, maybe 110. And just subjectively, I'm almost burning my finger on that, so it's probably at or below 130 Fahrenheit for sure. That there illustrates the heating of 5 watts after 4 or 5 minutes of running time under the best case scenario, because this is almost what's called a free air setup. A true free air setup, I want to elevate this slightly off the back there. That's still getting like 40 degrees over ambient, just parked there. So as a second illustration, let's loosely wrap some foil tape around the lamp there and see what happens with this insulated. Okay, that should keep a lot of the infrared energy reflected back into the lamp. Let's just give it another minute and see what this temperature rises to. Still looking at about 70 on the black background here. Then on this over here, up to 130, and I'm starting to smell something hot coming off of here now, so it's definitely rising in temperature a lot. So yeah, hopefully that illustrates it pretty plainly that, 5 watts may not be a huge amount of power, but it's definitely enough to produce some heat, and if that heat ends up confined, well, your switches or devices are going to warm up. Now, let's suppose we develop a resistive connection. We've gotten some water in our connector or in our switch, some corrosion is forming. We have a spade terminal that's a little bit loose because it's been vibrating for so long that it no longer makes a full solid mechanical connection. Let's suppose this goes up just a little bit. So this is case 1. Let's suppose in case 2, this increases a little bit to 0.1 ohms. Well, now we have the exact same thing for case 2. V equals 10 amps times 0.1 ohms equals, unsurprisingly, it's now double, 1 volt. And what just happened to power? Oh, the power we're dissipating in our switch body or connection or whatever just doubled to 10 watts. Well, we now have the voltage at just below the alternator nominal of 13.8 volts, and that's about where this lamp burns 10 watts. Black backdrop, Registering slightly warmer, probably because of heat spreading out from the lamp assembly, but only a degree. But over here, we're back to nearly a free air setup, and I'm getting 130, 140, somewhere in there. And if we were to wrap this up and let it go, it would rise quite a bit hotter than that pretty quickly. Now if this were a switch body, it can operate in that condition as long as it stays below the melting point of the plastic. But frequently, you get that little bit of corrosion or whatever in there, and that takes it out. This here is not going to continue forever because obviously at some point we start dissipating so much voltage across here that our load stops operating correctly, and so it may not even pass nearly as much current at all. So there's some trade-off there, but this is what happens. This is why resistive connections are bad, and this is why powering very high current accessories through a connection like this is not a good idea, even if everything says it's rated for it. So if you follow that, you can see why even a very small amount of resistance in the connection when you start connecting a high current load is not good. And you think about the light switch problem a lot of people have, well, what happens? You get water ingress, or you just have age and deterioration. Connections have vibrated a lot, so they loosen up a bit, and they become resistive connections. And so that eventually can melt down switches, relays, and other things like that. The one thing you can really do about it is if you've got a high current accessory you need to run on a regular basis, is install some kind of dedicated plug for it. And as an example of that, we designed and installed a rear power panel using an appropriate connector. You can also see that video on our channel. But in the meantime, let's look inside this heater and see what it is and why it draws power, because I like taking things apart, and these little random automotive accessories are kind of interesting. This part here is pretty straightforward. We just have a 12 volt accessory socket. We have an inline 15 amp fuse on the positive, cord into here, 3 settings on the switch. Center off, left is fan only, right is heater and fan. So this has been designed a couple different ways. You can install this like on your dash or whatever and then clip this on and just point it around, or if you want, you can pull this handle out and hold it like that, which is great when you're on the road because nothing says to a cop that you're a safe person like holding something like this while you're driving. And there we have it. We have a horizontal rotary fan here, also sometimes called a squirrel cage, but that's a fairly efficient way of blowing air, and so it's blowing air sideways, and it's going right through this front element here. Okay, so looking closer, here's the actual guts of it. Got the switch right here. When power goes to the heater, it must go through this overheat detector. And looking closely at that, 120 degrees C. So 120 degrees C is hotter than the boiling point of water, of course, so this here will get quite toasty. And this plastic will probably be smelling by then, but it's still below the melting temperature of ABS plastic, so that's to keep things safe. That normally is tucked up right in here, which puts it directly above this guy, which is then sitting there. Looking a little closer at this, though, we have 2 ceramic packs in there. Positive power, I believe, is fed in through the center here, and then the return, the 2 negatives, are on the outside. So both of these packs operate with 12 volts across them, and there's probably just a bit of nickel chrome heating element wire or something in there passing through that ceramic pack. But by containing it all in that ceramic pack, that prevents anything from ever reaching glowing temperatures, and so all the heat is then dissipated out into these aluminum fins. Okay, what did we learn about that heater? Let's go back to the 2 equations we were using earlier, Ohm's law and the Ohm's law power equation. Volts, current in amps, resistance in ohms. Power in watts, or technically volt amperes, but we won't go too deep into that today. Volts and current in amps again. Now we have a heater that is rated for P equals 150 watts. The way we substitute that back in here is we can say that 150 watts equals our 12 volt nominal times some current I. To cross 12 back over, we have to divide it out of both sides. So if I divide this side by 12 and this side by 12, then I'm left with 150 divided by 12 equals 12.5 amps. Well, now I can take this back into V equals IR, and I have V of 12 volts equals my I of 12.5 amps times R. And if I divide both sides by 12.5, on this side I am left with R equals 12 divided by 12.5. 0.96 ohms equals R. So I'm expecting the net resistance of that heater pack, which remember was 2 elements in parallel, to be roughly 0.96 ohms. As it happens, that's pretty close to what we found in there. Each of those 2 heating elements, which is basically just looks like 2 resistors in parallel like this because of how they were wired. When we measured it, each of these turned out to be just about 2 ohms. When you have 2 resistances in parallel, the total resistance is the sum of the reciprocals. So 1 over the total resistance is the same as 1 over R1 plus 1 over R2. In this case, I get a half plus a half equals 1/2 plus 1/2 equals 1. So even though this is 1 over R total, since it's 1, if I flip it over, I still have 1. So the total resistance here is 1 ohm. Checks out. Now, what kind of schematic did we find in there? Well, we start at positive because we have incoming positive from the center tip of the lighter socket. So plus 12 volts DC, and then immediately in our cord, just draw a fuse symbol here, we had a 15 amp fuse. And then coming into our device, we had our switch, and we're feeding the center terminals, and we could switch that left or right. We had 2 terminals over here, and right we had 2 terminals over here. Let's put this little symbol here, so this could go this way, it could go that way. This is what is called a double pole, double throw, DP/DT, but you might also see it referred to as a 2-pole, 2-throw. So 2 independent poles and 2 directions that it can be switched. Both of these positions here were connected in common to the fan motor circuit. So if we went left, we switched on the fan only because it would come to his circuit and there was nothing connected down here. If we went right, well, then this one over here would also feed 12 volts into our heater circuit. Before going through the heater circuit, however, it had to take a diversion through the little overheat detector, just put TH for thermal, and then it would go through our heater circuit, which just was 2 power resistors in parallel, sandwiched between aluminum, each of these being 2 ohms, together being approximately 1 ohm. And both of these circuits we turn out to negative, which is the sleeve of the lighter socket. Very simple device, but very practical. It does what it's supposed to do. The main limitation is to produce 150 watts at 12 volts. It has to draw 12.5 amps. And as we saw, it's really going to heat up the socket over here because that socket just isn't a great way to carry that much power. If this starts to melt down, it can take out the power socket with it. So these are great little accessories, but if you're going to run them long term, you need to come up with some sort of permanent wiring solution. Well, everyone, there it is. And I hope you now understand a little bit more about the best and safe practices for operating electrical accessories on your vehicle, especially if you have something high current, like say a high current power inverter or an electric heater that you like to use to preheat your cabin. There are some things that either you should use specialty plugs for them or you should use dedicated wiring, but don't just stick everything in the 12 volt power port and expect it to work consistently. Best case scenario, a fuse pops. But if you're running a high current load that is not drawing more power than it should, but is in fact overheating the connection, bad stuff can happen. And we do have a couple videos on wiring on this channel also, if you want to watch those and get some ideas on what you could be doing. Anyway, hope that it gives you some inspiration on how to make your vehicle a little bit safer and a little bit more versatile. Thank you for joining us again today. We'll see you again next time, whenever that is. Has anyone seen my phone?